Alright, so today we are going to do some example problems involving Biot-Savart law. Remember, Biot-Savart law plays the same role in magnetism that Coulomb's law plays in electrostatics. So let's consider a current element. So here is a current carrying wire, and let's consider some infinitesimal current element of length ds. Here, assume that the current is flowing this way in this wire. So the current element here will be tangent to the path and will be pointing this way. So that's the direction of ds. And let's say that we have to find the magnetic field at some point over here at point P due to this current element d of length ds, infinitesimal length ds. Let's say that the distance between point P and this infinitesimal current element is r, and the vector from this ds to point P points in this direction, and let's say that the unit vector is r hat. So r hat is nothing but the vector r divided by the magnitude of that vector. So the magnitude of r hat is basically 1. In this case, what Biot-Savart law says is that the magnetic field that is produced by this infinitesimal current element of length ds at this point P, let's call it dB, d sub B, according to Biot-Savart law, that magnetic field d sub B will be mu 0 over 4 pi I ds cross r hat divided by r square. Note that over here mu 0 is a constant, it's the permeability constant, and its value is 4 pi times 10 power minus 7 Tesla meter per ampere. Also, notice that the direction of this magnetic field due to this current element given by Biot-Savart law is in the direction ds cross r hat. So it is really perpendicular to both the current element ds and to r hat. So if you use your right hand rule, you will see in this particular problem ds and r hat are both in the plane of the paper. So ds cross r hat, according to your right hand rule, will be pointing into the paper at this point P, like this. What about the magnitude of d sub B, the magnetic field produced by this infinitesimal current element at this point P? Well, according to Biot-Savart law, that magnitude will be mu 0 over 4 pi I, the magnitude of ds, times magnitude of r hat, but remember the magnitude of r hat is just 1 since it's a unit vector, times sine theta, where theta is this angle between ds and r hat, divided by r square. So this is the magnitude of d sub B given by Biot-Savart law. Let's try to make use of this Biot-Savart law to find the magnetic field due to an infinitely long straight current carrying wire. So the magnetic field due to an infinitely long straight current carrying wire carrying a constant current I. So let's say here is my infinitely long straight current carrying wire carrying current up like this, and the current is I, and let's say we have to find the magnetic field at some point P over here, which is at a perpendicular distance capital R from this current carrying wire. Let's first take some current element d sub s at some point. Let's say if this is my origin, then let's say that the current element ds over here, which is in the direction of current like this, is at a distance s from this origin. So this distance here is s. Then, first of all, let's join this current element with point P here, and this is the direction of unit vector r hat, and the distance over here is basically r. And notice that this is what we call angle theta here. So in this particular case, and notice that our wire is infinite on this side and it's infinite on the other side too. So let's figure out what is the direction of magnetic field due to this infinitesimal current element using our right hand rule. So remember, the direction of magnetic field at this point P due to this infinitesimal current element will be given by the direction of ds cross r hat. So let's try it. So ds cross r hat, do you see that it's pointing into the paper because both ds and r hat are in the plane of the paper. So obviously the ds cross r hat vector, which is the direction of d sub b given by Biot-Savart law, will be pointing into the paper right here at point P. Okay, great. And notice that no matter where we choose the ds, whether we choose it here, 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 anywhere, the direction of magnetic field will always be ds cross r hat, and it's always going to be into the paper here. So that means all of these magnetic fields will add up, and the net magnetic field can be found due to the whole wire by doing an integral. So let's first write down what is the magnetic field d sub b just due to this infinitesimal current element at this point P. So that will be given by, according to Biot-Savart law, as dB is equal to mu 0 over 4 pi I ds sine theta divided by r square. Now the question is, what is sine theta? Well, if this is theta, notice that this angle here, since this whole thing is 180 degree, will be 180 degree minus theta. And notice that sine theta from trigonometric identity is the same as sine of 180 degree minus theta, which from this right angle triangle here from this triangle will just be equal to r divided by little r. In other words, sine theta will be r divided by square root of s square plus r square. Because from this right angle triangle, you can write this variable little r in terms of s and r. Okay, great. So if that's the case, then we can write d sub b as mu 0 over 4 pi I ds divided by r square, and r square itself will be s square plus r square. This is what I'm writing, r square is here. And then this sine theta here will become this r divided by square root of s square plus r square. So that the total magnetic field then will be integral of this. So B magnitude will be integral of dB. And remember, the direction is pointing into the paper. So we are right now only calculating the magnitude, and that will be mu 0 I divided by 4 pi, and then we have integral ds. We can also pull out r since it's constant, and s square plus r square times square root of s square plus r square is really nothing but s square plus r square to the power 3 over 2. And notice that here the integral will be, what will the integral be? Well, notice that it might be a good idea to first find the magnetic field due to half of the wire from origin to infinity and then double it. So really the magnetic field will be twice the magnetic field from 0 to infinity. So the integral here is 0 to infinity. If I just double it, saying that the magnetic field from 0 to minus infinity will give you exactly the same contribution, there also the magnetic field is pointing into the paper. Okay, great. So basically what we are seeing then is that B is nothing but mu 0 I r over 2 pi times integral from 0 to infinity of ds s square plus r square to the power 3 over 2. And this is an integral which you can do. I am just going to write down the answer for you. It's going to be s divided by s square plus r square to the power half, evaluated at infinity and 0. So what is that? Well, that's mu 0 I r over 2 pi. And if I evaluate this thing at infinity, a better way to write the same thing would be to write it like this. To write it as s, pull the s out, and then you can write it as 1 plus r over s whole square to the power half. And then evaluate it at infinity minus, if you like, just this thing evaluated at 0, and you can see if you put s equal to 0, this will become this. By the way, this is s square plus r square to the power half, this to the power half. And of course this is 0. But what is this contribution at infinity? First of all, this and this get cancelled out. And what you see is that if you put infinity over here for s, 1 over infinity gives you 0, and you really get 1. So this thing is nothing but mu 0 I r over two pi. Notice that actually I have forgotten something. I should have taken into account the fact that there was something in the denominator, and actually the thing in the denominator here is going to be 1 over r square. So I forgot the fact that when you do this integral, you will find that there is also a 1 over r square here, and that 1 over r square will actually cancel one of the r's here. So this comes from doing the integral. And so finally, actually, you will not have anything in the numerator here, because this is basically this, but you will actually get mu 0 I over 2 pi r. So that's the magnetic field due to an infinitely long straight current carrying wire. Later, we will derive the same exact results for the magnitude of magnetic field due to an infinitely long straight current carrying wire using Ampere's law, which is in the same spirit as Gauss's law for electricity, which helps you figure out the magnetic field due to symmetric current distributions easily. And you will see that we'll get the same exact answer for an infinitely long straight current carrying wire. Okay, let's stop to think about what would be the magnetic field at a distance r away from a long straight current carrying wire if it was semi-infinite. So if it was only from 0 to infinity. So in other words, if the magnetic field was only due to the upper or lower half of this current carrying wire, in which case the magnetic field is semi-infinite, in that case you can see that we wouldn't have put this 2 that we put down, and we would have found that the magnetic field will be half of what we found for this infinitely long straight current carrying wire. So for semi-infinite long straight current carrying wire, the magnetic field will be half of this value, which is for long straight current carrying wire from minus infinity to plus infinity. So in this case, the magnitude of magnetic field will be mu 0 I over 4 pi r. And of course, the direction is again given by the right hand rule. It's in the direction ds cross r hat. And what you will see is that in this case, where the wire is carrying current like this, and let's say this is the semi-infinite wire, and we are trying to find the magnetic field at point P at a distance r away. In this case, if this is the direction of current, then the direction of magnetic field is actually into the paper. And this is the magnitude. All right, so let's now look at another example. And this time, the example that we will look at will be magnetic field. This example problem will be for magnetic field due to a current in a circular arc of wire. Okay, what do I mean by that? Well, let's say that I have a circular arc like this, and here is the center of the circle, C, and the current in this wire is, in this arc is flowing like this, and it's a constant current I, and we have to find the magnetic field at the center over here. And let's say that this arc makes a total angle phi here. So from one end to the other, this angle is phi in radians. Now we also know that the radius of this circular arc is capital R. Okay, so the question is, can we use Biot-Savart law to find the magnitude and direction of magnetic field in this case? Yes, of course we can. So let's consider some current element ds, and notice that ds will always be tangent to the path in the direction of current. So here it's tangent like this, and you can see that if you're trying to find the magnetic field here, so magnetic field dB over here at point C, which is at the center of this arc, then the vector r hat is going to be like this. And notice that r hat is in the direction of radius of this arc, and ds is tangent, so the angle between these two is 90 degrees. So also use your right hand rule to do ds cross r hat, and you would see that the magnetic field dB here will be pointing out of the paper. So it's actually a dot coming out at you, which makes sense because ds and r hat are both in the plane of the paper, so the ds cross r hat vector, which is the dB, should be pointing out, perpendicular to the plane in which ds and r hat lie. Now notice that no matter which ds you consider, if you consider a ds here, again the corresponding r vector would be like this. So if this is your ds, then r hat will be like this. Again the angle between them is 90 degree. So, and again the magnetic field direction is coming out. So the magnetic field due to all of these little ds's will add up, and if you look at the magnitude of magnetic field just due to say one current element, that will be mu 0 over 4 pi times I ds times sine 90, because that's the angle between r hat and ds, r hat and ds anywhere, divided by, in this case, capital R square, because that is the magnitude of this distance of the point where we are trying to find the magnetic field from the current element, and it's the same everywhere. This is r, etc., no matter where you consider the ds. So then, and sine 90 is just 1. So basically the total magnetic field then will just be integral of dB, which is going to be mu 0 over 4 pi I r square. These are all constants, so I'm pulling them out, times integral ds. Notice sine 90 is just 1. And what is it? This is integral ds from 0 to phi. If we are considering some point here and the angle phi is 0, and then as you keep going the angle phi keeps increasing, and then it's all the way till the point when it becomes the angle becomes phi. And this thing is what? It's nothing but just r times phi. So if you look at this, you can see that this will be just mu 0 I 4 pi r square times this thing. I mean, one way to write this will be to say, well, this thing is, that's what I'm writing here. We can write this as r times d phi, because ds is r d phi, and then you're trying to find it from 0 to phi, and then if you pull the r out, this is mu 0 I over 4 pi r, and integral of d phi just gives you the total phi. So basically the answer turns out to be mu 0 I phi over 4 pi r. This is the magnitude of magnetic field due to a current element, due to a current in a circular arc of wire where the total angle is phi in radians. So this is the magnitude of magnetic field for this case. Now what happens if you have a full circle? So in other words, if you had to find the magnetic field at the center C due to current that is flowing around in a circle like this, in this case basically we can use the results that we just found, except in this case phi is 2 pi radians because we are considering a full circle. So in this case the magnetic field will turn out to be mu 0 I 2 pi divided by 4 pi r, which is nothing but mu 0 I over 2r. This is the magnitude of magnetic field, and you can see that the direction of magnetic field will be again coming out at you. And the direction of magnetic field is basically the same due to all the little ds's. They are all going to give you, just use your right hand rule and you will see that ds cross r hat will always be pointing out at the center of this circular current carrying wire. Alright, so let's look at another example. And this time the example that we are going to consider will be very similar to this magnetic field due to a current in the circular arc of wire, except that let's say this time we have something like this. So this example has some wire that looks like this. And in this case, let's say we have to find the magnetic field at the center of this circular arc again, such that this part of the wire that is carrying current like this part which is carrying current like this, and this part that is carrying current like this are such that this current carrying wire is in a straight line like this, and same as this. You know, if you extend this current carrying wire, this is along the radial direction, so it meets here at the center. And we have to find the magnetic field at this point C, you know, due to all of these three parts. B is equal to what? That's the question. So think about it. Basically, and we are given, let's say, that the radius of this circle is r. So this thing is r. Do you see that in this particular case, and let's say that we have been given that this angle here is phi. So in this particular case, basically we have three contributions to magnetic field at this point C, at the center of this arc here. So what are those three contributions? Well, we can call the contribution to this straight part contribution 1. This circular arc will give us contribution 2, and this straight part will again give us contribution 3. So the total B will be B due to part 1 plus B at this point C due to part 2 plus B at this point due to part 3. Okay, now let's see what are the contributions due to part 1 and 3 using Biot-Savart law. Well, in order to see that, let's just consider an infinitesimal current element here, d sub s, which is in the direction of I, which is like this. What's the direction of r hat vector? Well, r hat is basically along the straight line joining ds with c, but do you see that that's again in the same direction as ds? So if ds and r hat are in the same direction, I hope that you can see that b1 will be 0, because that's going to be integral mu 0 over 4 pi I ds times sine 0, divided by some r square, but sine 0 is 0. So this thing is obviously going to give us a 0. Similarly, look at the contribution due to part 3. Here, your ds is going to be in the direction of current like that, and your r hat vector is going to be, pointing towards the center like this, and this time the angle between ds and r hat is 180 degrees. This angle between ds and r hat. And so again, v due to part 3 will be this integral from mu 0 over 4 pi I ds sine 180 degree over r square. But again, sine 180 degree is also 0. So if this is 0, then this whole contribution is 0. So really these two parts don't contribute at all to the magnetic field at this point, because ds and r hat point in the same direction, or they point at 180 degrees to each other. So then the total contribution at this point at point C is only due to this current element, and we just figured out how to find the magnetic field due to that. And let's think about the direction. Well, notice that here ds is going to be pointing this way, and r hat is going to be like this. And so if you do ds cross r hat, you will see that the magnetic field is pointing into the paper, and that will be due to all the ds's that make up this arc here. And so the total magnetic field is pointing in, and its magnitude b will be just due to part 2, b2 the magnitude, and that will be something that we just found in the last part. It will be mu 0 I phi divided by 4 pi r. Let's consider the case where phi was 90 degree. If phi was equal to 90 degree, which is the same as pi over 2, then in this case the magnitude of magnetic field will be mu 0 I over 4 pi r times pi over 2, which is mu 0 I over 8r. Similarly, if phi was equal to pi over 4, in this case b would be equal to mu 0 I over 4 pi r times pi over 4, and that's equal to mu 0 I over 16r. Alright, let's try to do another example. In this particular case, we are going to figure out what is the magnetic field on the central axis of a current loop at a distance z from the plane. So this example is an example in which we are going to find the magnetic field on the central axis of a current loop which is carrying current I at a distance z from the plane. So basically here's the situation. You have a current loop. Let's say it's carrying current I like this. So here it's like this, here it's like this, here it's like this, and here is the central axis, and at some height z, at this point P, we want to know what is the magnetic field, both magnitude and direction, due to this current in this loop. So notice it is different from the previous problem, because in the previous problem we were trying to find the magnetic field right here at point C. This time we are calculating it at some other point P, which is at a height z from that other point C where we just found the magnetic field in the earlier problem. So in order to do this problem, it is much more convenient if we actually just look at the cross-section of this loop. By the way, let's say that the radius of this loop is R. So if we look at the cross-section of this loop through here like this, then the cross-section will look something like this here. Let me draw it for you. This point here will have a current coming towards us. This point here will have a current going away from us. And this is the radius R. So basically, I'm looking at a cross-section through the current loop of radius R. Okay, so now if we have to find the magnetic field at some height Z, here, this is the height Z, then we should be thinking about the contribution due to all of the infinitesimal DS's that make up this loop. So we can consider a little ds here, 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 etc. Let's focus on first on a ds right here, or in this particular view of it, I'm going to consider a ds right here, which is, in the direction of current coming out at us. And remember that R, vector R hat, will be like this. And this is the distance R from this point to this. And this is where we are trying to find the magnetic field, this point P. Now think about what is the angle between this vector R hat, which connects this little ds here, the little current element at this point here, or if you like here, with this point P. Think about it, like what would be the angle between, this is the R, this is the direction of R hat, and the ds is basically in the direction of current over here, or over here. You can think about both views. I hope you're convinced that the angle between R hat and ds is 90 degrees. And it's 90 degrees at all points. No matter where you consider the ds here, the angle is always 90 degrees. In other words, according to Biot-Savart law, you can say that the magnitude of dB is mu 0 over 4 pi I ds sine 90 degree divided by r square, where r is basically the distance from here to here. So this distance here is r. Now, I hope that you can also see that this r can be written as in terms of this r and the z like this. You can say that r square is equal to r square plus z square from that right angle triangle. Also, I want you to think about the direction of the magnetic field dB due to this infinitesimal current element. Think about the plane in which ds and r hat lie, and obviously dB will be perpendicular to it. Let's use our right hand rule. So do it with me. Put all the fingers of your right hand in the direction of ds, cross them in the direction of r vector, and you can see that dB should be perpendicular to, at this point, should be perpendicular to the plane in which r hat and ds lie. So dB will be something like this. Now, I hope that you can also see this is the dB due to this current element here, ds. What if we were to look at the contribution due to this, due to a ds here, which is, due to this part here, there is a ds here. What will be the contribution due to this little ds at this point here? Again, you can see that the magnitude of dB will be exactly what we found here. This time, if you do your right hand rule, you will see the dB cross r hat, instead of pointing like this, this time it will be pointing this way. So if that's the case, then let's say that if this is our y direction, we can think about two contributions to dB. One contribution to dB, which is, one component of dB which is along the y direction, which we can call dB parallel, and then there's another component which is dB perpendicular. And I hope that you can see that if I'm also looking at the contribution at this point P due to this, the current element here, then I have to join this like this, and I have to look at some, dB due to this particular thing, and that would have the perpendicular component that will cancel this perpendicular component, and whose parallel component will add up with this. So in other words, what we see is that all we need to take into account is the parallel component. So in other words, it's only the dB parallel that survives, because for every part of the wire there will always be another component another part of the wire that will cancel the perpendicular component. For example, if you look at some ds here, that will produce a magnetic field here that will be whose parallel component will be cancelled by a ds here. Similarly, if you look at something here whose parallel component will be cancelled by this thing, so there will be some ds here whose parallel component will be cancelled by another ds across from it, etc., etc. So basically what we are saying is that the only magnetic field that survives is the parallel component of magnetic field, and so the direction of net magnetic field at this point is definitely pointing up. All we need to now worry about is the magnitude of magnetic field, and that magnitude is going to be the integral of dB parallel. So what is dB parallel? Well, notice that if this, let's call this angle alpha. If this angle is alpha, then I hope you can see that from this right angle triangle here, this angle is 90 minus alpha. That means this angle is alpha. That means from this right angle triangle, this is 90 minus alpha, and that means from this right angle triangle, this angle is alpha. And if that angle is alpha, then dB parallel is nothing but dB cosine alpha. So this is nothing but dB cosine alpha. In other words, B can be written as integral, and dB we already know here. So making use of this, we can say it's mu 0 over 4 pi I ds, and sine 90 is just 1, divided by r square. R square we just found is r square plus z square, so it's r square plus z square times cosine alpha. Now the question is, what is cosine alpha? Well, let's think about it. Notice from this triangle here, cosine alpha is nothing but r, capital R, divided by little r, and little r is nothing but capital R square plus c square. So in other words, cosine alpha is nothing plus r divided by little r, or r divided by square root of r square plus c square. So let's plug that in over there, and what we will find is that dB parallel B, which is equal to dB parallel integral, will turn out to be mu 0 over 4 pi I integral ds over r square plus z square times cosine alpha, which is r divided by r square plus z square square root. And notice that this square root just means to the power half. So basically B then is mu 0 over 4 pi I times this whole thing. Notice also that r square and z square do not change, so we can actually pull them out of integral. They don't need to be inside integral. All of these things here are constants, so we can just pull them out. And also this times square root here gives us a power of 3 halves. So basically what we have is r divided by r square plus z square to the power 3 over 2. And then we have integral ds. What do you think should be the limit of the integral? We are doing the integral over all the little ds's that form the whole loop, so the integral should be from 0 to 2 pi r. And that just gives us 2 pi r. So b turns out to be mu 0 over 4 pi I r times 2 pi r, that's what we get from the integral, divided by r square plus z square to the power 3 over 2. In other words, we find that b is equal to mu 0, pi and pi get cancelled, 2 and 4 give us just 2 in the denominator, mu 0 I, this r and this r give us r square, divided by 2 r square plus z square to the power 3 over 2. This is the final answer for the magnitude of magnetic field on the central axis of a current loop at a distance z from the plane. And I already told you the direction of the magnetic field will be basically away from the perpendicular bisector. So basically along the axis of the loop. Basically we found that the direction would be, so if this was the situation, remember the direction of magnetic field at this point P at a distance z, and this is the radius of the loop. At this point the magnetic field direction was like this. So this was the direction of B, and this is the magnitude that we just found.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.